So today, our speaker, Aaron, he'll talk about the introduction and evolution of object segmentation. He is currently a fourth-year computer science student at De La Salle University under the BS-MS-CS honors program. So yes, you can take it from here, Aaron.
Hello, everyone. Good afternoon to everyone, and thank you for coming into our lecture here in CIVI. So, today I'm going to talk about object segmentation. So, just to show what we're going to talk about today, we're going to start off explaining what object segmentation is and the history behind the field of object segmentation, how it was made, the different architectures and networks that served as the foundation of object segmentation, and finally, metrics for evaluating these networks and current applications for this computer vision task. So without further ado, let us start with defining what object segmentation is. So object segmentation is under a broader field of study called computer vision. So that is what we are focusing here in DLSU CIVI, our computer laboratory. So it is all about leveraging image data such as pictures and videos to solve real-world problems. Under computer vision, there are three main categories of different tasks that we explore. So these fall into image identification, object detection, and object segmentation. So image identification here, yeah, it's sort of blurry, but I really wanted to highlight how image identification works. So we have one main subject for an image, and what we are trying to do is to have our um, neural networks identify what exactly the main subject of that image is. So for example, here we have planes, dogs, and frogs. So there's only one subject per image, and we are just trying to identify what that subject is. So this is in contrast to object detection, where instead of having just one subject, we have multiple subjects in an image. And the goal for your machine learning model is to identify the different positions or locations of these subjects and to assign for them the correct labels. So as we can see here, we are sort of evolving from the idea of image identification to now having multiple subjects. Now, finally, the topic of our lecture for today is object segmentation. So this, once again, expands upon the task of object detection, where it is also trying to detect multiple objects or subjects in an image. However, instead of just detecting the bounding box, which is what we are looking at here, so the general location of an object segmentation aims to actually assigning a segmentation mask or giving a specific outline or contour for that object. So that is what object segmentation is. And now we are going to talk about how it has evolved over time. So as we saw there, it is a fairly advanced computer vision task. And before we actually started using machine learning models to do these tasks, we actually had several traditional methods to perform object segmentation. So this was way before using machine learning. So these can be grouped into three categories: threshold-based, edge-based, and region-based. So what are the differences between them? Let's start with threshold-based. So threshold-based object segmentation, what we do is that we take an image right here, and then we say, let's just take a specific range of values to isolate from that image. And then that's how we generate our object segmentation mask. So this is very similar to if you guys have ever used something like Photoshop or GIMP or MS Paint, the one tool in those photo editing softwares, where you click on an image, you take their specific color, and then it shows you the outline of the colors that you're trying to get. So that is basically what threshold-based object segmentation is. Now, this technique does have limitations, as with all of the traditional methods. So first, it assumes that some objects only have similar values as a whole. So as we see here, I have some examples here of objects that have um, fairly similar ranges of values. When I say values, for images, you can also think of that as color. So in here, this box, it is only mostly red. This glasses container, it's only mostly black, and this remote's only mostly black. Same with this laptop, it's only mostly gray. Well, the question arrives is, what happens if you have objects with a variety of colors? So now it becomes very difficult to isolate just that object alone. As we can go back to the example with the cannonball, I didn't fully get to isolate the entirety of the cannonball because I can of the cannon, I meant, because as you can see here, the shading is a bit off for the shadows, and also here for the part with the moss. So that is one limitation of threshold-based segmentation. Additionally, threshold-based segmentation, it also assumes that distinct objects have different range values from one another. So what I mean by this is that when you are looking at different types of objects, it is very easy to distinguish them apart. So for example, here we can clearly say this is a blue umbrella, this is a green umbrella, this is a slightly bluer umbrella, red umbrella, etc. As well as here the different colors of kites. So it is very easy to tell an orange kite apart from a pink kite. Well, what happens then if your different kinds of objects all have very similar colors? So for example, here, the leaves of the radish versus the leaves of a carrot. Sure, you could say like there's a bit of purple here, but they are both mostly green. Now, what if we were to include trying to differentiate between these herbs right here and these herbs right here as well? So they also have very similar ranges of colors, so it makes it hard to differentiate between the two. Same as here as well. So it is even more difficult in this case because we are now looking at different varieties of tomatoes. So as you can see, all the tomatoes basically are some sort of reddish orange. So you're going to need to have a different technique than just threshold based to differentiate among them. And finally, it also has a hard time segmenting objects that blend into the environment, which this specific limitation we will see is going to apply also to the different other different traditional methods as well. So this is especially troublesome for objects that actually camouflage into their environment, such as these. The fruits are very hard to distinguish from the leaves, as well as the zebras from the environment. So I'd just like to ask if I'm going a bit too fast for anyone. Please just comment in the chat box for any questions that you might have, and we will answer them as we go on to the lecture. So now we're moving on to edge-based object segmentation. So instead of isolating specific ranges of values and using that as our method of segmenting objects, we are now isolating the edges between objects and then using that as our method of segmentation. So how are these edges actually determined? So once again, this also depends on the values or the colors of the objects. So it assumes that objects have widely different values near its boundaries. So a boundary is, as you can see here, the difference between one object where it ends and where another object begins. So if we look at this box, near the edge here, it has mostly red values, red colors here at the edge. And at as like the object of the box ends, it transitions to another range of values. So mostly gray colors here at the edge here. So that is how generally edge-based segmentation tools work. So once again, this technique also has a hard time segmenting objects that blend into the environment because, as we explained before, it depends on, I mean, it assumes that objects can be distinguished from the colors in its environment. So the question now happens is, what happens if the objects itself has a very similar range of colors to its environment? That's where edge-based segmentation um, gets its difficulties. And finally, we are going to region-based thresholding. So this way, this method, it segments images by continuously subdividing the image until the regions have been finalized. What do I mean by that? So as we can see here, let's start with this main image here. So region-based segmentation, what it does, it continuously subdivides the image into different regions, okay? And the method of subdivision actually depends, once again, on the range of values. So it also depends on the range of values near its boundaries. So instead of just detecting the edge, what it does is if a specific edge is near a boundary of an object, so like this again, widely different values again, that's where it's going to make the subdivision. And that's how it isolates the segmentation mask for a specific object, like here, this skier. So because it also has the same limitation as edge-based segmentation, it also has this same problem here, where it's also having a hard time segmenting images that blend into the environment. So now, because of all of those traditional methods, we are now going to move on to the specific networks that were developed that could actually address these methods. So these segmentation networks actually started because of deep residual learning. So if you were to check out the DLSU CIVI YouTube channel, there's going to be a lecture there also about deep residual learning, which is one of the prerequisites of this lecture. So if you wish to actually touch up on that, you can check it out. But because of that specific innovation, network performances started to improve, and now it was actually viable to apply segmentation for machine learning models. So we're actually going to discuss two main segmentation models that are, I would say, like the foundation of object segmentation. So these are fully convolutional networks, FCNs, and mask RCNN. Okay, so let's start with FCNs first. So as we can see here, it's called a fully convolutional network because back then, there already were innovations that were using convolutional neural networks as part of its training. However, these existing networks, they weren't fully convolutional. So they still relied upon using some pre-processing techniques like the traditional methods that I showed earlier in order to actually perform segmentation. So fully convolutional neural networks removes all of those pre-processing techniques or traditional methods, and instead opts to use just convolutional neural networks to perform segmentation. So as you can see here, let's look at a deeper dive within the architecture here. So here I have my own diagram here of FCN, and I would like for us to focus here at the top. So FCN here is the actual network itself, and what it relies on is fully convolutional operations. So in this part, from 3x3 conv 6464 all the way to here to CB, this CB is called a convolutional block. And what it does is that it like continues to extract features inside of the image. And actually, like as you can see here, this sort of architecture that slowly makes the image smaller and smaller, but increases like the number of channels here. So that is what the convolutional blocks are doing. It's increasing the number of channels while decreasing the dimensions. So it does that so that it is going to be able to learn more and more about the image and the different features of different objects there. So this part here, all of this is what encodes that features. And finally, once all of those features have been learned and encoded, it's going to go into this decoder block here. So this one corresponds to here, the pixel-wise prediction in the original paper. And what that does is that since this encoding class decreased the dimensions of the image overall, what's it going to do? It's actually going to like increase the dimensions again into a full image. So all of these are just for actually predicting the the specific pixel labels. So, and then these parts here is what actually increases the dimensions of the image again. So that operation of increasing the dimensions of the image, that is called upscaling here. Okay. Is everyone with me so far here for FCNs? Oops. Okay. All good. Okay. Thank you. So once again, all of these operations here, they are all fully using convolutional neural networks. Even the upscaling here, these are also fully convolutional, as well as all of the training here, all of that is only relying on convolutional neural networks. So why is that important? It's important because if you actually think about it, if you have a model with um, modules that aren't convolutional, then you're going to need to have another method of training for them. So either another method of training or actually no training at all. It's just like hard coded that that's what your network's supposed to do. Or you would need to actually assign them as hyperparameters. So if you have a model that's fully convolutional, you can do something that's called end-to-end training. So that means you can, all of these parts here, the encoding part here, the convolutional blocks, the decoding process here, all of that is fully trainable and fully learnable via gradient descent. So that's what makes it very powerful. So I'd also just like to explain how the model makes its predictions. So what it does here is actually assign specific values to each pixel in the image. And it's just saying, okay, this pixel belongs to this specific class, or this pixel is just a background, or this pixel is belonging to a cat or a dog, or etc., etc. So that's how this architecture makes its predictions. And that specific type of prediction of predicting what type of class each pixel belongs to, that falls under semantic object segmentation. So just to further expound what semantic object segmentation is, generally you could like divide segmentation tasks into either semantic or instance object segmentation. Semantic segmentation, what it does is just assigns labels to each pixel, and it determines like the best class that fits for that specific pixel or object in an image. So here I have an example of just like a bowl of fruit. And let's say our model is actually trying to look for the oranges in this bowl of fruit. So it finds these segments and then it assigns to them one type of class. And it says these pixels belong to the orange class. However, for instance segmentation, it actually separates the different instances of objects that it finds from one another. So this is very useful for counting tasks and object tracking. So instead of just saying, okay, all of these pixels belong to oranges, all of these are oranges classes. Okay, it can actually determine like, okay, this is orange number one, and this is orange number two, and this is orange number three. So that's what makes it distinguished from semantic segmentation. However, as I said, FCNs only perform semantic object segmentation. What actually brought about instance object segmentation was mask RCNN here. So this allows you to actually perform what we've shown, instance object segmentation. And here, I would actually like to spend a bit of time talking about how mask RCNN came about, because it's actually a really useful story for everyone that's actually starting to do their research, especially those that wish to improve upon existing architectures, because mask RCNN is built on like three different object detection networks before it finally became an object segmentation network. So hopefully this story will actually show you how you could actually perform research that improves upon another architecture as well. So let's start with the foundation of mask RCNN, which is RCNN itself. So RCNN means regions with CNN features, as we can see here from these figures. And what it does, it adopts image classification models. So those that only determine the main subject for an image, it adopts them and it allows them to perform object detection tasks, or detecting multiple images inside multiple objects, inside an image. So there are three modules to this. The first one is the region proposal network, as we can see here. And this region proposal network, this is hard coded. This is not a machine learning technique here. So it uses a selective search algorithm. This is not trainable actually. And it's just a specific algorithm that performs region-based segmentation. So if you would remember the region-based segmentation, it would subdivide the image and then determine the segments here. And then after that, after dividing the images into segments, it actually makes a bounding box, or a box that surrounds each segment. So every run of the region proposal network, it generates about 2,000 regions. So numerous regions. And after taking all of those regions and getting all of them, it feeds each one of them to a convolutional neural network. So it takes each of those regions, which have like a specific subject in mind, and then it turns them into a square image. It just stretches them and turns them into a square. And then after that, it feeds it into an existing image classification model, like here for examples like VGG19 or ResNet. And then that's how it turns the object detection task into image classification, because now each image is being fed into an image classification model. And what's special about this is that they actually modify the architecture of the existing models as well. So instead of having like their last layers here, which are responsible for predicting classes, they just modified it to allow them to predict the specific classes that they have and one extra class for the background. And it takes that and then it turns it into a feature vector that has 4096 dimensions. Okay, so that is happening for each and every region that it detects, which, keep in mind, there are 2,000 regions, so this runs 2,000 times for every image, ganun. So fairly fairly time complex, right? Very slow. And then finally, for each class that they want to detect, so another for loop, they are going to feed it into a support vector machine, which will calculate the intersection over union for all boxes. And then it's going to use something called greedy non-maximum suppression. So what that just means is that um, using the intersection over union, which I will discuss later, of all the boxes, if any of the boxes have like lower threshold, it's just going to be discarded. And then any boxes here that have the highest confidence, that's going to be the final detection label here. Okay, so that's actually how it detects the images here. As you can see here, there's like one big box here. So that was what was given by the region proposal network here. And then from the from the support vector machine, it determined that it is a background image. So it is actually being removed because we don't necessarily need to like label that it's to the background. That's why they remove it. And then here, for this person here, as you can see, they have a 0.991 a score. And then that is going to be the final um, detection here. Okay. And that's what RCNN does. Now we're going to move on to fast RCNN. So this one now improves upon RCNN, and it improves upon the limitations we saw. So first off, it forwards the region proposals one at a time. So that was referring to like the 2,000 different regions that it determined. It's going to feed that each one of them into a convolutional neural network. And then for each class, it's going to feed each one of them again to a support vector machine. So very time costly. And additionally, multi-stage pipeline training, you have to train the CNN and the support vector machine separately. Additionally, you have to train this support vector machines that it's using um, to in two tasks. You have to train it to only use the appropriate features taken from the convolutional neural network, and you have to train it to actually determine the right classes. So fast RCNN updates all of this by, instead of forwarding each image, that region that it found one at a time. It's going to forward it all at once, and it's going to take away the support vector machine in favor for a convolutional neural network. So this is what I'm saying about how research in architecture usually goes. What you do is that you look upon the features and the characteristics of your specific network. You do some testing, and then you find out, oh, there's a bottleneck here, or it's actually slow because of this, etc. And now you think about, okay, how can I improve upon um, this architecture? And our fast RCNN actually improves it by um, taking into account these specific limitations. So, as we said before, fast RCNN, it, instead of forwarding each region one at a time, it's going to forward it all at once. So what it does is, instead of extracting the features later, it extracts the features of the image immediately and then feeds it into the selective search algorithm. And then it still takes all of those 2,000 different regions, and then it uses a separate layer called an ROI polling layer. So what that does is that it just takes all of those different regions, it turns them all into feature vectors, and then it just puts them all together into one big feature map. It just actually just combines all of those regions together into one map. And then finally, instead of using a support vector machine, in here, it actually uses two different convolutional neural networks. One that uses a softmax operation to get the label of each class for each region. And then another one called a bounding box regressor. Because remember, at this time here, for the region of interest polling layer, itong ROI polling layer, they are all in the form of feature vectors. So we need to convert all of those feature vectors back into regions and bounding boxes to show in the image. So this is what that regressor does. And then finally, now we move on to faster RCNN. So we are still in object detection, keep in mind. However, as we saw here, we've already taken away the support vector machine in RCNN and replaced it with a convolutional neural network here in fast RCNN. And now we're forwarding all of the regions at once. However, we are still using the selective search algorithm for fast RCNN. Faster RCNN takes that limitation, and then it says, instead of using that selective search algorithm, let's just go all in with using convolutional neural networks. So it modifies this region proposal network into only using convolutional neural networks. So this is kind of the same story as well with fully convolutional networks. Yung the FCNs that we saw earlier. So by utilizing a fully convolutional architecture here, you are now able to train the network end to end with one training process only. So this modified region proposal network, what it does is that it takes the regions here, the feature vectors here extracted from the CNN feature extractor, and then it takes only a specific box of that in that feature map. And then it slides that box across the entire feature map like a tiny box. And then inside that box, it's taking that as an input for another convolutional neural network here. Okay, so that's the n by n sliding window, that box that actually goes through the entire map. And then for each input found inside that box, it's going to run it to this CNN layer, which is going to perform, going to take different scores of each pixel in that box. And then that score actually says, okay, how likely is it that I can find a specific class inside that box? So it's just like a scoring of likelihood of the different labels that can be found inside that box. And then this reg layer here, it just tells you the coordinates of that specific object being found inside of that box. And now finally, we move on to mask RCNN. So here comes the instance segmentation. So it improves upon RCNN by taking that architecture that we've seen already, that fully convolutional architecture, and then it allows it to do instance segmentation. Okay? So what it does here, I have like an entirety of the evolution from RCNN to mask RCNN. So what it does from faster RCNN here to mask RCNN is that this last module here that is responsible for classifying the different labels of each bounding box and then giving you the different coordinates of every bounding box. It just adds another module here that is also built upon an existing convolutional neural network like ResNet or FCN, and then it takes that and uses it to output a segmentation mask. Okay, so that way, it's like a natural course of evolution that allows it to perform object segmentation here. Okay, is that clear for everyone so far? How um object segmentation evolved over time and how these foundational networks actually came about. Okay, so thank you for everyone's responses. And now finally, now that we've talked about the different neural networks that are being performed, I used actually these foundational networks, we're going to talk about how to judge its performance. So now we're going to move on to the metrics being used in object segmentation. So how do you choose a metric for object segmentation? In general, when you're choosing a metric for a task, it has to be able to appropriately rate the quality of the predictions. So you do not want to choose a metric that doesn't accurately model what you want it to do. You want that metric to say, okay, it's the metric should be high if it's doing what I want it to do, right? And it should be low when it's not doing what I want it to do. So let's start with this for an example. Accuracy, precision, recall, and F1. So I'm sure that a lot of you have already heard of these different metrics because these are usually used for classification tasks. So right, when you have a prediction that's being performed and the model actually predicts wrong and sometimes it predicts the right label. So it produces this called a confusion matrix, which shows you the statistics of all of its predictions. So through positive means, it predicted that the label is true, and when you check actually like the ground truth, it is also true. False negatives, it predicted that it's false, but it's actually true. False positives, it predicted that it's actually true, but it's actually false. A true negative, it predicted that it's false, and it's actually false. Right? So that's how you read a confusion matrix. And you derive these different metrics, accuracy, precision, recall, using these formulas here. So you take all of these numbers here and then you apply these formulas. So accuracy, it's just checking how accurate your model is, how many things it got right over everything else. Precision, this specifically focuses on getting the true positives in the model. recall specifically focuses on getting the true negatives. So if you want your model to actually focus on correctly identifying the true positive labels, you would usually look at precision. And if you focus on actually getting the recall, you're actually looking into like the the true negatives of the model. In the F1 score, it's kind of like a balance in between precision and recall. So I've said all these things about these four metrics. However, they're not actually really appropriate for object segmentation because these are for classification tasks, right? So one image per class only. A prediction can be incorrectly or incorrectly classified. So these are like really niche in the field of segmentation because you need a specific task that happens to be classification that only happens to need segmentation as well. Kind of like that. So maybe you're like detecting tumors in cells and you're detecting it one at a time, which is not actually ideal, something like that. But who knows, that might be something you might need. So this is like very niche for segmentation because it will not model what if there's multiple objects. Um, how effective your segmentation technique is, how effective is it in actually capturing the structure of the object you're trying to detect or your segment. For that, we have other metrics. For example, here, pixel accuracy. This is a metric that's commonly used. So basically, it just counts the number of pixels that has correctly been labeled over the total number of pixels in your image. So just that straight up. So here I have an example image here of a red cross, a red X. The ground truth usually would look like this, just an image that has 0 or black in the background and 1 or white in the class label that you want to detect. And the prediction would give out a segmentation mask that's kind of like this. And then you just count how many things it got right. So this wrong, another one wrong, and actually another one wrong here. So this should actually be 22 over 25 instead of 23. So around 89%, something like that. Uh, However, this also has a limitation where it doesn't separate the accuracy of prediction for each label. So pixel accuracy back in which I showed, that's only really useful if you only have one specific class you're trying to detect or segment. However, if you want to detect multiple classes, you're going to want to use mean pixel accuracy. So mean pixel accuracy here, it takes the accuracy across each and every class. So here I have an image that has multiple classes as well. So the red cross here, and then this green part, and then your ground truth or would look like this. So a background here, labeled 1 for the cross and a label of 2 for the green shape, the green letter T here. And then an accuracy would look like this. Your prediction would look something a bit like this, where you have predictions for the green class and the predictions for the red class here. And then you're going to tally up the accuracy for each class here. So how many parts of the red cross did it get right? It got 2 wrong, so 7 over 9. How many parts of the green T that it got right? So 3 out of 4. And then finally, how many pixels of the background did it get right? 11 over 12. Okay. And then finally, you just take that, all of those um, accuracies, and then you average that. And that is your mean pixel accuracy. So that takes into account the accuracy of segmentation for many different classes as well. Now, what if we also want to take into account the shape? the shape of your segmentation mask. So that is where these last two metrics will come handy. So it is intersection over union, or IOU. So basically, it depends on the structure of your it's going to depend on the structure of your prediction. So what it's going to do, it's going to take your prediction and your ground truth, and it's going to overlay them together. If once overlaid, if your prediction and your ground truth is perfect, as in you got the ground truth 100% right, your intersection over union is going to be exactly 1. However, if you get the ground prediction completely wrong, that it's going to be a 0. Okay? Intersection over union, because that's the actual formula for it. You take the intersection of your prediction to your ground truth here, y, and then all over the union, which is the union of your ground truth with your prediction here, and then that's your score for that image. So this is being applied for each image, and if you want to measure the overall network performance using IOU, you're just going to like average the intersection over union of all images, of all of your predictions to all of its corresponding ground truths. Okay, so this one very widely used. This metric is very widely used because it also takes into account the shape of your prediction as well as how close it is, like this, like the specific pixels as well of your prediction. Okay. And finally, this one, if this one has structural similarity index measure, this is also being used. However, this is more of being used for very, very, very specialized tasks that need how do I say this? These are usually used for tasks that need a much more closer look into detail than IOU, because sometimes there are tasks such as like medical imaging where your images are like very small and microscopic even. So in those tasks, they needed a measure that actually is very precise. So that is what SSIM is being used for. So what it does, it takes into account three metrics into the evaluation. So the luminance, the contrast, and the structure. So these are just like the different variables being used. So M here refers to your ground truth, and then N is your prediction and your ground truth, and then you just take the average, the variance, and the covariance. So common statistical measures, and then you just apply it to this formula right here, and that's how you get your SSIM. Okay. And finally, lastly, we're going to talk about just the current landscape of object segmentation today. So I really want to talk about like 4 different um, um, fields in object segmentation. So how object segmentation models have been improving over the years, how to actually create object segmentation datasets, and 2 special fields that are here, which are camouflage object segmentation and zero-shot object segmentation. Right? So object segmentation datasets. So these, when you are improving upon an object segmentation dataset, it kind of also follows the same flow that we've showed um, earlier in the lecture with how RCNN evolved to fast RCNN, to faster RCNN, and to mask RCNN. So that same flow chart of examining the architecture of existing models, determining bottlenecks in performance and possible limitations of the models, and proposing alternatives that could solve those bottlenecks and limitations. That same flowchart is still flowing today. Okay, let me give you an example here. So this is actually what I'm working on right now. This is a model called RiskNet. So never mind what exactly each of these architectures and modules do, but just know that this specific module here, that when you see a DFD, that um, stands for a depth feature decoder. Depth meaning it requires special depth images that can be obtained from just a specific depth camera that is very expensive. Okay, so what I'm actually looking on right now to do in my research, I'm asking, okay, is it possible to replace this specific module here so that I do not need to use a depth camera anymore? So by doing that, I could make the object segmentation network much more accessible to the public. So you can use it without even utilizing a special depth camera and maybe even like just a mobile phone instead, right? So that same line of thinking of let's look at the limitations and figure out what can be done. That's still being applied here for object segmentation models today. And finally, sorry, next let's move on to the data sets. So specialized data sets for segmentation are usually very scarce. So if you want to like focus on a specific field like imaging or like crops or maybe like camouflaged objects, it's usually scarce and very few to find. So you actually really have to look um, really hard for them. Or sometimes it's like locked behind a paywall, or you have to message the author first. So sometimes actually these data sets might not even exist, right? If like it's a very, very, very new field. So what other researchers are focusing on is actually finding ways of creating data sets for these fields as well. So there are three main ways: either creating the data sets through, I don't know, naturally taking pictures of these objects in its environment and manually labeling the different segmentation masks for it. Synthetic creation. So this involves taking pictures of environments that these objects might be found in, and then synthetically taking existing objects and their object segmentation mask and just blending it into the environment, sort of like this. Parang it's like copy pasting it and photoshopping these objects programmatically or generatively. So using AI like GANs to generate these images. And now there's also what's being called zero-shot segmentation. So this is a very, very new field in object segmentation, where instead of focusing on a specific segmentation technique or specific classes of segmentations to look for, or classes or objects, it just teaches the model how to perform segmentation. So right, it's a very new technique. So instead of learning, okay, you should learn how to tell a horse apart from its environment. You're teaching a model, okay, you just need to learn how to tell things apart from its environment, sort of like that. And finally, this was discussed earlier, so medical imaging. So this actually distinguishes itself from normal segmentation because, as I said before, the images are like very microscopic and usually not very clear here. and you have to really look for the minute differences with the images and its environment. That's why there have been like many specialized architectures for medical imaging. And finally, my line of research here, camouflage object segmentation. So this focuses on objects that blend into their environments, because these objects, first off, they require like different metrics in order to judge like the effectiveness of segmentation for their camouflaged objects. And number two, the data sets here are very like few and far between. And finally, it's you're going to need like different training techniques and different architectures, because as I said before, the objects actually blend into their environment. Okay, so that concludes the end of our lecture here. I now open the floor to any questions that our listeners may have.
Hi, thank you for the presentation. So for me, I have a question. If ever someone were to begin studying object detection, where's the best place to start?
Mm. So detections doc or segmentation did they mean?
Object detection muna. Let's
Object
start with object
detection.
detection.
So I guess the best place to start studying object detection. For me personally, I learned as well from DLSU CIVI. So I think I'm able to send a link later, but they also have a really great um playlist there that also guides you into setting up like your own object detection network, and like explaining the different metrics and like best practices in making object detection networks. Yeah, so that's for me because I really did learn from the CV YouTube channel as well.
I see, I see.
So I have a comment here from Kate. So she says here that what others do is data mining to scrape data from online sources to make their own data sets. Yes, Kate, that's also a valid technique for creating here object segmentation data sets. So what they do, it's actually a part of here set in natural creation. They would take pictures or sometimes get it online, and then they would still need to pre-process or like manually add their own segmentation mask that say, okay, this is the orange here, and then this is the another orange, etc. Like that. Oh, okay, we have a question from Magallanes Fords. You can open your mic.
Hi, good afternoon. I really like the presentation, but this might be outside the scope of your presentation. But I was interested if you can give me advice on how we can train these computer vision, yung object segmentation uh in your current setup. So currently, I have a project also that I'm interested in. But I'm since my laptop is only CPU, wala siyang GPU. I'm having difficulties on training my project. So can you tell
Mm,
me how can I further improve on the training process of my model?
yes. Okay. So your problem, Ferds, is parang low power environment right now. Is that the issue?
Yes.
Yeah. Okay. So what I usually do in low power environments, um, well, you can't really improve upon the performance or anything, especially if you're like using pre-built networks or models. So one pointing. So um, checkpointing for object for model training. So um, right, the training process, it goes through several epochs or instances, right? Just several cycles. So what you do, um, once it's done running one cycle, you save the model and all of its weights. That way, um, for example, when you're low power environment, it crashes, or while it's in the middle of training, it just stops training altogether. What you can do, one these checkpoints, you save the model after it's done training for one epoch, right? And when if ever your computer crashes or your environment crashes, things like that, what you can do, you can just load the weights or the state of your model after training that one epoch, and then continue training from there. So that's a really common workaround. Aside from that, I would also look into like cloud-based solutions. Probably like Google Colab would be a good place to start. So Google Colab. Because yeah, it's cloud-based. So it's not necessarily your system anymore. You're using the computational resources of Google to train your network, something like that.
Okay, got this. Thank you for your answer. Appreciate it.
You're welcome. Yeah. Also, if anyone else is also, ayun, thank you, Doc Jet. You can also use Kaggle for free compute. So that's also something to look into. Additionally, if anyone else is interested in learning how to train their own object segmentation and like different ways and best practices of trading, we're also going to have a workshop here next week that that's applying all of these techniques as well. So what we've learned here about object segmentation, we're going to then apply in our own training for object segmentation models as well. Okay, any more questions?
So guys, last call for questions. If any are interested.
We're going to do the second half in Jupyter notebooks. Yes, I will provide a notebook and the data set that we're going to use. Okay. No more questions, guys. Oh, and yeah, here just references. If you guys want to check out like the different papers.
Okay, guys, so if there are no more questions, thank you so much for joining today's workshop. Um, so yeah, I guess you guys can go na, and we'll send the recording dun sa emails. Thank you all so much.
Thank you, everyone. Have a
Thank you.
nice week.